This is David Small with Team Small Robots coming at you with another video. Today we're doing something a little bit different and we're going to talk about a spreadsheet. Woo! This is my Team Small Robots bot calculator, or the Bot-ulator, as I came up with after 2 seconds of name brainstorming. But this is a spreadsheet that I've used basically for every single robot I've ever designed. Gimli, Highlander, Kelpie, Sonokram, Puka, even Banshee uses this spreadsheet. I've just been slowly upgrading it. I've given this to some of my friends who are also builders and they seem to like it a lot. So I figured, hey, I'll button it up a little and distribute it to everybody to use. So this is just going to be a quick video explaining how everything works. I'm trying not to edit too much here, so bear with me as I just ramble on about how my spreadsheet works here. So I'll have the link to this in the description. You can go ahead and click that. It'll open up a window just like this, but you won't be able to edit anything because that's my version of the spreadsheet. You'll need to make your own version of the spreadsheet. So to do that, you just come up here to File and then make a copy. You can call this whatever you want. I usually call it the name of my robot. So like, hit make a copy. And then this will be your own version of the spreadsheet and you'll be able to edit these values to your heart's content. So down here at the bottom left, you can see we have a few different sheets. There's the weight one that we're looking at now, but there's stuff for drive, the weapon, and battery life as well. So we'll go through these each one at a time. Starting with the weight calculation sheet, we've got the weight calculation table and the conversion calculators. So let's start with the conversion calculator because that's easy. Basically, all you do is type in a number for one unit and it'll spit out whatever the other unit is. So say you have a battery and it's 24 grams, but you're measuring your robot in ounces like I am here. So let's say it's 24 grams, that's 0.847 ounces. So I would grab this value, copy, Control C. I'd go over to the battery section and I would paste that in there. And you can see it updates everything. So one thing to note actually is if you copy something and you just hit Control V directly, things will break because you are not just pasting the number, you're pasting the entire formula, the formatting, all that stuff, and you don't want to do that. So if you select the cell and then do Control Shift V, all it does is paste the number. So if I grab this again, Control C, paste that in, Control Shift V, it just sticks the number in as text without the formula attached to it. So the other thing to note is that this entire table is unitless. You can use whatever unit you want. So I use ounces, but if you want to use grams, you can go ahead and use grams. All you would have to do down here is change whatever your target value is. So since I'm doing ounces, 48 ounces is 3 pounds. That's how much a beetle weight weighs. If you wanted to do grams, you would just need that amount in grams, and we can actually use our calculator here. So if I put in 3 pounds, that is 1360.8 ounces. So I'll copy that with Control C. And then as we just learned, Control Shift V to paste it in. And now that is our value. The problem though is all of these values are ounces. So I'd have to convert all these to grams as well. But when you're first getting started with this spreadsheet, pick whatever unit you want and stick with it, and you won't have to go back and undo everything. So I'm going to change that back. As you can see, each item in the list has its own weight here, and then it automatically calculates what the percentage is for the rest of the robot. So for example, the hardware is 5.9 ounces or 12.67% of the robot's weight. When you're trying to save weight, you can kind of just search for these big numbers and then say, oh, look, my weapon motor is almost 10% of the entire robot. Maybe I could get a smaller one, or whatever you want to, trim fat the best you can. Then it'll give a summary of each subsection's percentage at the top, as well as a sum of all the pieces in that subsection. So my chassis is 38.54% of the entire robot, et cetera, et cetera. The other thing to note is that this section down here gives you the remaining weight. So since I'm not quite at 48 ounces, I have 0.91 ounces remaining. So it's nice to just know how much wiggle room you have. Say I were to add another part that's really heavy. This is my backup battery and it weighs 10 ounces. So now I'm -9 ounces remaining. So that basically means I'm 9 ounces overweight. My total weight is 57. I definitely exceeded that 48. So it'll also tell you how much overweight you are. So I'll go ahead and get rid of that. Another thing to keep in mind is anything that's bold is something that I'm calculating automatically. So don't type in your own percentage. That's something that's being calculated on its own. Anything bold, just leave it alone. So to those of you brand new to combat robotics and you're wondering where you get all these values and stuff from, I have a few examples laid out. The first example, of course, is to just weigh it, put it on the scale. Things like the battery or speed controllers, you can just drop on a scale or use the value on their website and just type that in directly using the appropriate calculation converter if needed. Then the other example would be you have a part that you're having made from your robot and you need to know how much that weighs. So most CAD programs will tell you how much a part weighs. So if we open up Puka here, and I want to know how much this inner rail weighs, I can come over here. This is the part. I want to know how much it weighs. In Fusion, I can right click it and go to Properties. This, of course, assumes you have the correct material selected. So this is UHMW, and it comes out to 1.043 ounces. Fusion used to have a feature where you could just click on this and it would copy it, but they got rid of it because we're not allowed to be happy. So I'm going to take that number. It's already in ounces, so I don't have to worry about converting anything. And I would go over here to my inner rail. And as you can see here, instead of just typing it, since there's two of them, I created a formula with the equal sign. So 2 times that amount, because there's 2 rails and they're identical. Don't do this if they're not identical. And then that'll spit out this value for your inner rails. So that one's pretty straightforward. The other thing is I like to group my parts together in ways that make it easier to weigh. So like the hardware is an example of this. I have every single bolt of this robot in CAD, so I know to the gram what this robot is going to weigh. If I go to my hardware here, that's every single bolt in the robot. If you open this up, you can see it's split even more between various hardware subsections. I really like my subsections. I watch people in YouTube videos, they have Fusion open and they have 5,000 components here that they're scrolling through, and I just don't understand how people work that way. It drives me insane. Anyway, since they're all grouped together, you can weigh the subsection in Fusion. So all of my hardware is 6.47 ounces or 6.457 ounces. So I would grab that value, put it into the spreadsheet like that. So let's type that in. It was a number vaguely similar to that. It doesn't really matter for this example, but that does bring up the purpose that you do need to keep updating this so that you know you're still within weight. You don't want to use outdated information. So the other example is a 3D printed part, and that's kind of the biggest reason to use this spreadsheet is because you can't accurately predict how much a part's going to weigh in CAD. Your slicer needs to calculate the infill in specific ways, and your CAD system just doesn't account for that. So what I do is I export the part to my slicer. So here I have Puka's backplate / switch mount / motor guard mount thing. This is printed out of nylon G at 30%. So if I were to slice this, I would get a handy weight down here in grams, 25.46. The thing to note, though, is there's a lot of stuff on this print that's going to be cut out. There's a brim, there's that edge around, and there's some supports. All of that is going to be removed. So for this purpose, I'm going to disable anything that isn't just the part. So now there's no brim, no support, nothing like that. And I'll reslice it. And now we have 24.4 grams. So that is how much the part's going to weigh. There is a little border that it's doing, but that's not enough to matter. So 24.4 grams. We're going to go back here, 24.4 to convert that to ounces. And that's 0.861, which I would copy and paste and then into back. So let's do that. Whatever I had before was heavier, so that's great. Control-Shift-V to paste. Now everything's updated. We've got 1/2 ounce to play with now. So that's how this works. It's all pretty straightforward. Obviously, you're not going to use the same component names as me. This is going to be tailored specifically to your robot. So delete whatever you need, add whatever you want, and make it fit what you're doing. So next up is the drive section. So this is all about the drive system, how fast your robot goes, your motor speed, your motor pulleys, your gearboxes, all that good stuff. So as you can see here, there's not just one robot's worth of information, there's a bunch. And this is so that you can compare various drive systems. So here's Puka, here's its battery information, the kV of the drive motors, wheel diameter, all that good stuff. And then it'll spit out some useful information here. But say, you know, you wanted to compare motors or something like that. Maybe Repeat Robotics just came out with a new drive motor. It's the Peter Speeder. So I want to see what Puka is like with the Peter Speeder. So I'll copy and paste that. This is the Peter Speeder version of Puka. Make that a little bigger. That's way too big. So what I'm going to do is copy this information, paste that in, and then I'm going to grab all of this and extend it. And this is the same calculation because we haven't changed anything. So let's say the Peter Speeder is 3000 kV, and that's what makes it so fast. So now we can see how much faster our wheels are turning, what the speed is. Like we're almost double now because we went from 1500 to 3000. So you can play around with all these numbers. I also have a section for gearboxes and pulley teeth. So the gearbox ratio is how much reduction there is in total for the gearbox. So if the Mega Sparks that Puka uses are 21.5 to 1. So I just put in 21.5. It divides the speed by 21.5. That's how that works. So if you had a 13 to 1 gearbox, maybe that's what the Peter Speeder is. It's even faster. Yeah, we're at 48 miles per hour. Good luck catching me. I got Peter Speeders. With that, you can also output into belts if you want. Puka doesn't use belts, or it does use belts, but it doesn't use belts for reduction. So that's why it's just 1 to 1. I have a sample belted bot in here that uses a 12-tooth pulley on the gearbox and then 24 teeth on the wheels. That adds an extra 2 to the ratio, which is why it has a ratio of 20 instead of just 10, because the 12 to 24 doubles the reduction. If you don't use a gearbox, you know, just make that one. This would be 1 to 1 to 1 is just the motor speed. This is the speediest Peter Speeder config that you can buy. And that's obviously a little ridiculous, but I really like the name Peter Speeder. But yeah, so that's the drive comparison. Jumping into the weapon system calculations table, you can see this is very similar to the drive section. It's basically the same thing, but for the weapon, where you can add as many rows as you want to compare different setups. So like these first two, they're exactly the same, except this version uses a LIHV battery, and then this version just uses a regular LiPo. There's your motor RPM, weapon RPM, tip speed, and kinetic energy. So, you know, just bumping up your voltage slightly gives me 30 more joules, which is pretty interesting. You've got your weapon motor pulley teeth, and then the weapon itself pulley teeth count. So this does the reduction calculation for you. You put in the diameter, give it the MOI, and it'll calculate all this stuff for you. So MOI is something you're going to have to grab from your CAD program, and I can show that off real quick. So back to Puka. What you want to get is everything that spins, all of your spinning mass. So I'm going to open up the weapon here, and I've got the Puka drum right here. So let's isolate that. So if I right click this and go to properties, and then like, you know, SolidWorks, Onshape, I'm sure they can all do this too. You've got your moment of inertia at center of mass right here, or at the origin, whichever one of these is correct. In my case, they're both the same. And that'll open up this list of moments. Then you want to select the one that your weapon is going to be rotating around. So if you look up here, the x-axis is what goes through the drum. So I'm going to use the IXX option. This is an ounce mass inches squared, which is not correct. If you go back to the spreadsheet here, we're looking for kilogram meters squared. So in Fusion, all you have to do is go over here and change the units to meters. and then grab the properties. Moment of inertia, and it's 8.194 times 10 to the negative 5. We'd grab that value and then paste it in the spreadsheet here. So 8.1934 or whatever to 10 to the negative 5th is that obnoxiously long decimal. And with that, we're able to calculate stuff like kinetic energy, which is pretty cool. If the event you're going to has a tip speed limit, this is how you can make sure you're not going over it. If you have a tip speed in mind that you want to target, then you can kind of use this to see what you need to change to get to. So maybe I want to pump this up to 200, so I'll do a 20-tooth pulley instead. Now we're just at under 200, so just play with the numbers to get a system that works for you. I really don't use this too much, but it's got some somewhat handy things in here. So the first thing we have is life estimation. So you've got your battery milliamp hour value. So this is a 1000 milliamp battery, weapon amp draw and drive amp draw. So it's just drawing 1 amp between these two. So if the battery is 1 amp hour and you're pulling 1 amp, the battery will last 1 hour. Something more realistic would be like a 650 milliamp hour battery, and then you use like, I don't know, 8 amps, 4 amps. And this will barely get me over 3 minutes and 25 seconds. So what makes this difficult though is this needs to be your average weapon draw, not your peak, not your minimum, but your average. And that makes it extremely difficult to kind of guess what you're doing. So the only thing I kind of use this for is I will put a watt meter on the robot and crank it to like 50%, and I'll see how many amps that is. So this will be 0. Maybe my weapon pulls 15 amps at 50%. So I go, oh, okay, I can only last 2 minutes or 2.6 minutes if I keep the weapon at 50% the entire time. So don't do that. And then I would label this as like 50%, just so I know. So yeah, you can play around with those numbers to give you a very, very vague ballpark estimate of how long things will last. Then the other table down here is kind of the reverse. So you have an amount of current that your robot produces. What battery do you need to not hurt the battery? Because if you exceed your battery's current limit, you're going to puff it and damage it, and you don't want to do that. So this is something I use mainly for my flippers, because usually the limitation is peak current draw and not battery life, if that makes sense. Like Highlander, my flipper ant weight, all it has to power is 4 N20s. The flipper takes no electricity at all. So that's something like 6 amps total for all 4 motors. If I ran a 50C battery, all I need is a 120 milliamp hour battery to power Highlander, because it doesn't use that much current. So it's kind of a handy tool to see what the smallest battery you can get away is. Obviously, if I had a spinner, I would be pulling way more current than this, and the battery would drain very quickly. So this is more of a peak current to not damage the battery kind of calculation rather than battery life. That's it. That's the Team Small Robots Bot-ulator. This is version 1.0. I imagine as I post this and get feedback, there's going to be lots of things that you guys want to change, lots of things that I want to change. So keep an eye out for updated versions of this spreadsheet. I'll keep a link in the description for you to look at, and you can try it out for yourself. If you have any questions at all, it could be about Google Sheets, it could be about how I CAD robots, it could be a fusion question, just anything at all, feel free to drop a comment. I want to make sure I'm coming across as clear and concise as possible. Then, of course, if you have a suggestion on how you would make this spreadsheet better, go ahead and let me know, and I can include that in the next update. So that about does it. If you enjoyed the video, make sure to give it a like, subscribe for more content like this, and I'll see you guys next time.